Alright, welcome to Warnow's Mad Integral Dash. So I'm just going to work a bunch of integrations with you, integrals with you today. And we're just going to work a bunch until I get bored with them. So let's practice taking some antiderivatives. For example, let's say we're taking the antiderivative of sine of x plus 3x dx. This is just our straightforward integration rules. What function's derivative is sine? Well, we should know that the antiderivative of sine is just going to become negative cosine of x. The antiderivative of 3x, we add 1 to the power, so we would get 3x squared over 2. Don't forget the child, C1. Don't forget your C1 right there. I feel like the Mandalorian. Let's take a look at another one. Let's look at a little bit weirder one. Still sine of x, but it's going to be sine of 2x minus 3 dx. Now this is a little bit different because this has an inside function, so this is our composite function. So we're going to be using u substitution. We're going to let u equal 2x minus 3. So that's going to replace my 2x minus 3. To replace my dx, I'm going to write the differential, take the derivative with respect to x, and we get 2 dx. Solving for dx, we get du over 2. I can rewrite my integral now as sine of u du over 2. By bringing out that 1/2, we now get 1/2 sine u du, which I can integrate this pretty easily. 1/2 sine of u plus c1, and I just replace my u with 2x minus 3. So we get 1/2 sine 2x minus 3 plus c1. These, as you notice, don't take very long. Alright, so let's have a little bit more fun with definitely some, let's get a little bit triggerlicious with it right now. What if I have the antiderivative of secant theta tan theta d theta? Oh no, we work with x's, not thetas. It's no real secret. This is a rule because we know the derivative of secant theta tan theta is just secant of theta. So, other way around, that's terrible. Sorry about that. The derivative of secant theta is secant theta tan theta. Notice I made a mistake. That happens. Don't panic. Going back there to get my answer. Well, I'm going backwards. So this becomes secant of theta plus c1. Now, how can we make this more challenging? Make it a u substitution. So what if I did the same problem, but this time I did secant of 3 theta tangent of 3 theta d theta? Well, now we have a composite part. So we have an inside function. So we have to take care of that first. And to do that, we use our u substitution. Remember, u is always normally the inside function. So if I let u equal 3 d theta, du would be 3 d theta. Now, if you accidentally call that dx, the AP is not going to stress much about it. So we get d theta equals du over 3. So when I rewrite our integral, we're going to get secant u tan u du over 3. Bring out that 1/3. So we get 1/3, let me write that in black, 1/3 the secant of u, the tangent of u du. And I can integrate this. The antiderivative secant tangent we know is secant, but we got that 1/3 this time. This is what the composite does to it. This is what our inside function. We just get 1/3 of our answer here. We get 1/3 the secant of u plus c1, which of course is 1/3 the secant. Well, u is 3 theta plus c1. And there's our rule for this. Very easy to do. Alright, let's take a look at some more examples here. Alright, let's do some trickier u substitution problems right now. So, let's try the following. What about the antiderivative of 3x plus 10 to the 12th dx? Oh no, I don't want to expand this, but I can use u substitution. By letting u equal the inside function, we would get du equal 3 dx, and that's going to replace my dx, which is going to become du over 3, replacing my differential. So I can now write this as u to the 12th du over 3. And this is a lot easier to integrate, so I don't have to expand it. And bringing out that 1/3, we get u to the 12th du, which becomes 1/3 u, whoops, 1/3, getting ahead of myself there, u to the 13th over 13 plus c1. Simplifying it, that's 1/39. I can replace u with my 3x plus 10, don't forget the power, 13 plus c1. And there's our antiderivative right here. Alright, so what if we try another one here? Let's see here. What if we did something like the antiderivative of cosine 2x over 1 plus sine 2x squared? Okay, that escalated quickly. First off, I'm going to rewrite this. There's no quotient rule, so I'm just going to go ahead and rewrite this. Cosine 2x times 1 plus sine 2x to the negative 2 dx. Again, this is just a u substitution problem. Look, it's basically this. If you don't know the basic derivative rule, it's most time going to be u substitution until we start learning those other integration techniques. So u here will be 1 plus sine 2x, my inside function. The derivative, be careful of chain rule, becomes 2 cosine 2x dx. See, this is what you want. You see this cosine 2x, this cosine 2x? You want those to cancel. And they will if I solve for dx. Du becomes 2 cosine 2x. You can start seeing if I replace this dx with this du, the cosines will cancel. And that's what you want to be able to see right there. Rewriting our integral now, we would get cosine 2x times u to the negative 2 du over 2 cosine 2x. Again, those cosine 2x's cancel like we said. The 1/2, I can factor that out. U to the negative 2 du. And I integrate 1/2. This becomes u to the negative 1. Remember, we're adding 1 over negative 1 plus c1. Or negative 1/2. I'm going to put this on bottom. 1 over 1 plus sine 2x plus c1. And there's our antiderivative. Whew, that got ugly. But still, it took the same, it really took the same, even this really ugly one right here, it took the same number of steps pretty much. No matter how ugly they get. Alright, this is one that always gets a few people. What if we did this? The cosine of the square root of x over the square root of x dx. This is now a trickier one. So we ask, well, this again, there's no quotient rule, so this has to be u substitution in this case. So I look right here. There's my inside function. So there's my u. So my u would be root x. Now we should know the derivative of root x is just 1 over 2 root x dx. We see it a lot. Just memorize that. Dx then would be 2 root x du. And I can now substitute in. We would get cosine u over root x. What is dx being? 2 root x du. The square root of x's cancel. If these don't cancel, you've messed up. Go back and fix it. The 2, be careful, it's not a 1/2 this time. It's 2 times the antiderivative cosine u du. Or now what function's derivative is cosine? Sine. So this becomes 2 sine u plus c1, or replace your u, 2 sine root x plus c1 right there. We're just going to do a whole bunch of these together. Look how fun we are having, how much fun we are having. All right, so let's take a look at another example. Let's go back to kind of a simpler one. What if I have something like the antiderivative of 4x cubed minus 2x to the 5th dx. Now this is not a chain rule right here. This is not, So this is just a straightforward power rule. And my rule says add 1. So I get 4x to the 4th over 4 minus 2x to the 6th over 6 plus c1. I can leave it like that. AP is okay with that. But if you simplify it, x to the 5th minus 1/3 x to the 6th plus c1 right there. Now, one that tends to get people is something like this. What if I did x times the square root of x dx? Well, a lot of times people think, okay, it's got to be u substitution. No, not in this case, because I can write this as x to the 1/2 dx, and that when I add those powers, we get x to the 3/2 dx. So integrating this one, we now get x to the 5/2, add 1, times 2/5, because we're flipping it, plus c1 right there. Easy breezy. What about something like this? Let's try this one. The antiderivative of, let's do sine of x to the 1/2 times the cosine of x dx. Easy. Well, what's my u going to be? This is a u substitution because it's not like this one where I could just multiply them together. Cosine and sine are different bases. See, here my bases were the same, so I can add them together. But here we can't do that because sine and cosine are different bases. So we have to use u substitution here. U is going to be sine of x, the inside function. Its derivative is cosine of x dx. So we get dx is du over cosine of x. And again, what you want to see is that this cosine of x matches with this cosine of x on bottom. And it does, which means we can simplify this pretty easily. We get u to the 1/2 cosine of x du over cosine of x. Those cancel. And we're left with u to the 1/2 du, which I can integrate that u to the 3/2 times 2/3 plus c1 and just replace u. 2/3 u, which is sine of x, to the 3/2 plus c1. There we go. All right, so let's take a look at one of those algebraic substitutions we saw in our notes yesterday. So let's see here. What if I have a problem with this? X times the 3x plus 1 cubed dx. I could use algebraic substitution here. I'm going to let u equal the inside, 3x plus 1. My du is 3 dx, so dx is du over 3. Now we could just expand this one, but I'm going to go and use the algebraic substitution because it's kind of fun to do. And what I'm left with is x times u cubed, thanks, I work out, du over 3. Now my problem is we cannot have x and u in the same problem. So I have to somehow replace x. Well, to do that, I'm going to use algebraic substitution. And what I mean by that is I know that u is equal to 3x plus 1. Therefore, x can be written as u minus 1 over 3. And I can substitute that now in. And we would get u minus 1 over 3, u cubed, thanks, I work out, du over 3. I have two constants. I can factor both of these out to give me 1/9. And I'm going to distribute u to the 4th minus u cubed, thanks, I do work out. And my final answer, we get 1/9, keep it simple, u to the 5th over 5 minus u to the 4th over 4 plus c1. And now my last step is I'm going to replace my u. So we get 1/9 u to the 5th. Well, u was just 3x plus 1 to the 5th over 5 minus 3x plus 1 to the 4th over 4 plus c1. You don't have to distribute, just leave it alone. All right, anyway, we just did a whole bunch of examples. I hope you guys enjoyed it, and if you need to, watch these again. See you soon. Bye-bye.